I've talked about microwave kinetic inductance detectors. These are the detectors we use to look for planets around nearby stars. They're extremely sensitive photon detectors. But what we haven't gone into a ton of detail is what they look like. They're actually these little LC resonators, which is an inductor and a capacitor hooked up together, and they have a resonant frequency. You can think about it as a certain vibrational frequency that they shake at, that's in the gigahertz. When a photon comes in, it hits that little inductor in the oscillator, and it changes the frequency of that oscillation, and that's what we measure. But to measure it, we actually have to send in a probe tone, which is a microwave signal, at the resonant frequency of the device. Say it's 4 gigahertz. We'll send in a microwave tone at 4 gigahertz, and then we have to watch what happens to the phase and amplitude of that signal. So today, our graduate student, Jenny here, is going to tell you about the electronics we use to read these MKIDs out. And the really hard part is we're not trying to read out one, we're trying to read out 2,000 on a single wire. And then for our MEC camera, we do that 10 times for a total of 20,000 pixels of readout. And eventually we want to get to megapixel scale. So the stuff that Jenny is going to tell you about today is going to be how we're going to scale up to those huge arrays in the future.
Right, so the key trick that we use is something called multiplexing. So each of the different MKIDs has a specific frequency, and you can essentially put all the frequencies close together and separate them out using specialized electronics very similar to what's used for 5G and 6G wireless or cell phone communication.
All right, so now let's go into the lab and take a look at some of the hardware before we get into the firmware. All right, guys, so mostly you've seen us talk about fridge stuff, but we do a lot more than that in the lab. So today we're going to have our senior graduate student, Jenny, here, tell us about her thesis work, which is on the readout. This is how the MKIDs actually get read out with electronics.
Yeah, so I'm excited to tell you a little bit about the electronics work that we do here. I'm standing in front of our main readout board. This is called a RFSoC, or RF System on a Chip. The first RFSoC was released right when I started my PhD in 2018, so it was a cool opportunity to be able to learn how to use this new technology. Essentially what it is an electronic warfare device, is how I like to think about it. There's a lot of forms you have to fill out when you download the schematics for this board, but it can produce and receive radio frequency signals, so that's really useful for us with communicating with our devices in the fridge. We use a technique called multiplexing, so very loosely, many people can be talking on the phone next to each other or using the same spectrum nearby. Using similar techniques, we're able to just put a bunch of different MKID pixels in the fridge to try to make a big camera and spread out and acquire all the frequencies in real time using a device like this. I'll just point out some of the key features. It's on right now, so you don't want to touch it while it's on. But these little black things here, these are the memory of the board. So if you think about a regular computer, these are the RAM. So the way this works is it's a specialized kind of customizable computer called a FPGA, which stands for Field Programmable Gate Array. And so there's an FPGA, and then there's a regular CPU on there kind of next to each other. So 4 of these little black things are the memory for the FPGA, and then 4 of them are the memory for the CPU. And everything is contained under this little fan here. So this is the actual RFSoC chip right here. And then all the other components on the PCB are just things to basically manage the power and to get the data to these output ports here. So right now it's connected in loopback, so the data going out just goes right back in. But when we wanted to read out signals from the fridge, we'd take data out from this SMA port and connect it to this back panel here. It would go all the way through the fridge, and then it would come back in and be read out on the board. So I mentioned this device is an FPGA, and what that basically means is it's a super specialized computer where you can actually design the actual processes that are happening, and you can program it to do a bunch of different tasks in parallel. So right now I'm showing you a view of the device, and all of these little blue squares that are highlighted are cells on the computer that are active and that we're using. One of the major challenges with making a design that's this big is something called timing. And so you can kind of think of all these little cells as little highways that are routing ones and zeros on the chip. And when the highways there's too many of them and they get too full, you get this issue with congestion and routing, and this software can't find a solution to do the algorithm that you want in the given clock cycle that you need. And so it's been a big effort, but I'd like to point out that this design is showing that all the timing constraints are met. So it's currently making timing, which is really, really awesome. And I can show you guys some of the individual blocks next. I'll highlight some stuff in this design. This is where the software has decided to place the memory cells on the FPGA that are used to generate the waveform that we send out to the MKIDs. So sometimes when we're looking at how our FPGA file was synthesized, it's useful to highlight different pieces of the design and see sort of where they are. So this one here is the trigger system. So that's what actually is monitoring the photons and figuring out the energy. The actual DSP processing that separates out all of the MKIDs and down converts them is like the majority of the design. So I'll highlight that section next in green. So that's, as you can see, is basically the whole chip.
All right. So Jenny is our most senior graduate student now in her 6th year. So what are the parts of being a graduate student in the physics department that you like, and what are some of the things you don't like?
The thing I like the most is probably just having a lot of freedom to work on sort of whatever I want to do. I think this stuff is super interesting. It's more kind of electrical engineering, but I've had the flexibility to work on it despite being in physics. And so it's super cool to be able to try to adapt these new technologies to kind of modern physics problems.
Yeah, Jenny is also probably our most engineering slash industrial focus. She's done internships at Xilinx and Google during her time at UCSB. What kind of interesting things did you learn from working in industry as opposed to in an academic lab?
Well, it was certainly nice to be able to work with people who have like 20 years of experience working with these technologies. So it was kind of cool to see how people can build up that sort of knowledge. I would say just general project organization was something that I learned in industry, like how to use GitHub to organize these projects. And there was a lot of working with people across time zones, and so that was kind of interesting, like learning how to work with people remotely. There was one point that I had a developer like take over my computer and like do something on the FPGA like through my computer over a conference call, so that was kind of interesting to see.
So you've got a shirt that advertises someone. Would you like to shout out to a certain furry friend who has an Instagram page?
Yeah, shout out to my dog, Cosmo. He's got an Instagram at Cosmo the Space Frenchie. He just kind of adventures around Santa Barbara, loves going to the beach. He's at daycare right now, so I'm going to pick him up with this shirt and hopefully give him a little laugh.
The dog gets fed better than my children, that much I know.